about how atoms are constructed, let's talk about how all of the atoms and all of the elements are outlaid in the periodic table. So here's a copy of your periodic table, and there are a couple of things that I'm going to write on this periodic table. I'll tell you if I want you to write any of these things down on your table, but for now, watch what I'm doing. You can always refer to this on the lecture notes screen later on. Okay, there are a whole bunch of different types of elements, and they're all organized on the periodic table in such a way that they're kept separate. There is this blue line on the table, and this is what's known as the staircase, or the line that separates between metals and non-metals. So everything to the left of this staircase is a metal, and from now on capital M is abbreviation for metal, and everything to the right is a non-metal. As you travel towards the left, away from the staircase, your metallic properties increase. Okay, so all of the metals, or the elements that are touching the line are what are called the metalloids. That green's a little hard to see there. Metalloids have properties of both metals and nonmetals, and depending on who they react with, can behave either as a metal or a nonmetal. Metalloids are particularly useful in industry in the field of superconductors. So the metalloids are things that are touching the staircase. This group in here all of these elements in this group right here are what are called the transition metals. They're called the transition metals because while you're working your way through these elements, you're making your transition from more metallic properties to more non-metallic properties. So that's why they're called transition metals. The interesting thing about these transition metals is that they can behave in a lot of different unique ways. If you take a look at your periodic table, take a look at element number 26, iron, and you'll see iron's elemental symbol here, and right above that there are 3 numbers in black that say, because it might be a little bit hard for you to see those, 3, 2, and 6, and the 3 and the 2 are in bold print. These numbers are what are called oxidation states. So when these transition metals are bonding with other elements, they can have all these different oxidation states. Oxidation state is a fancy word for charge. We'll be talking about these transition metals in pretty great depth in just a moment. Okay, now I want you to take a pen or a pencil, and I want you to write some numbers above each of these groups as I'm doing here. We'll actually not use Roman numerals, we'll use regular numbers. So right above the hydrogen group, I want you to write a number 1. Beryllium is group 2. Skip all over the transition metals. Boron is 3, carbon is 4, nitrogen is 5, oxygen is 6, fluorine is 7, and helium is 8. These blue numbers are what are called your group A numbers. I know that there are a whole bunch of numbers and Roman numerals here on the table. That can get confusing, so I just want you to write these numbers above those elements on your tables. So these are the group numbers. If I asked you what group number is arsenic in, arsenic is element 33As. Arsenic is in group 5. Okay, so those are your group numbers. And now, let's see. You obviously have to do this on one periodic table, so we'll try to write small, just to make things more clear for you to understand. I'm using a separate one. Now I want you to write some other numbers. Plus 1 over hydrogen, plus 2 over beryllium, plus 3 over boron. Over carbon, I want you to write plus 4 / minus 4. Nitrogen is minus 3, oxygen minus 2, fluorine minus 1, helium is 0. These are the standard charges for each of the elements in these groups. So if I were to ask you to find chlorine, tell me what group number it's in and tell me what its charge is. Chlorine is here. It's in group 7 and it has a charge of minus 1. Okay. So have all that information sitting out for you on your periodic table for our next topic. Why do bonds form? Well, bonds are formed by the interaction of different atoms' electrons. And the reason why bonds form in a general way is to satisfy what's called the octet rule. The octet rule states that each atom strives to have 8 electrons in its outer shell. Okay, now if you go back and look at your periodic table and look at your group number, the group number is the same number of outer electrons, or what we call in chemistry valence electrons. V-A-L-E-N-C-E electrons. I apologize for my penmanship. These outer electrons, or these valence electrons, are the only electrons within your atom that are going to participate in any bonding. So it's important to know how many valence electrons each particular atom has, because the purpose of them bonding is to get 8. Let's take a look here at group number 8. If your purpose is to have 8 electrons and you are in group 8, you've already satisfied your purpose. You can think about the octet rule as sort of winning the lottery. If you've already won the lottery, you don't need to go to work. Let's say you're one of those people that won that big Powerball thing where you won, like, let's say you won the 368 million or whatever it was a couple weeks back. You know, after taxes, so you're left with what, almost 200 million bucks? You probably don't need to work. We're not talking about wanting to or philanthropic work. We're just talking about the need to work. All of the elements in group 8 have already won the lottery. They have 8 valence electrons. This group is called the noble gases. All of these elements are gases. That's why their letters are red on your periodic table. And they're called noble because, like nobility in times of old, they didn't have to work. They could live lives of ease because they didn't have to do daily chores. And the reason that they're called noble gases is because none of these elements actually form compounds with anyone else. They don't bond with each other, they don't bond with anything else because they already have 8 valence electrons. Krypton, element 36, is a sort of an exception. Krypton can bond with fluorine, but you have to add so much energy that it's not practical to even try. I think you have to increase your temperature to like something like 10,000 kelvins, which is, you know, approaching sun type heat. So for all intents and purposes, noble gases do not react. If something does not react, it's called inert. So all of these gases are inert because they already have fulfilled the octet rule. Okay. So you can determine the number of valence electrons by looking at the group number. Okay, let's do some examples of that. Okay. Pause your movie and identify how many valence electrons you have for each of these elements, then come back and see if you've got the answers right.